Good evening. Today is day 11 of Math 133. We're going to talk about the Chapter 5 review, and we'll do some more on the sample midterm. Last time we talked about the midterm. So if you weren't here during Thursday, the 12th, you're going to want to make sure you watch the recording because we talk about what to expect for the midterm. I also sent out an email that had a PDF with information on it. So if you were here last Thursday, then you heard all of that, so you're good to go. Okay. If you do have questions about the midterm, or anytime you have questions about anything, feel free to stop me or message me on Remind. So I will take a look and answer those messages. So, um, if you email me, that's fine too. I just don't check my email as often as Remind. Um, anyway, yeah, so the sample midterm is different from the midterm, right? The sample midterm is a worksheet, and we're going to turn that in. We're going to be working on that together. The midterm itself, that's going to be happening the week of February 26th. Okay. Okay, but for today, we are doing the Chapter 5 review. We're going to be talking about probability. That starts on page 390 in your course pack. You don't need to click on the Chapter 5 review worksheet in Canvas. I don't know why they put the link there, but like there's a link with all of our data sets. There's no data set for Chapter 5. So, let's just jump to page 390, okay? Page 390. And just like our other, worksheets that we've worked on before, we're going to go through. I'll give you some hints that'll help you with studying to get ready for the midterm. And then we'll go back through and we'll fill out anything we missed. So, a game at a fair consists of tossing a fair three-sided die. A game at a fair consists of tossing a fair three-sided die, sides one, two, three, and then spinning a fair. How many times can we say fair? Fair wheel with three equal colors, red, yellow, or green. You're going to play the game once. Okay. All right, construct a tree diagram to show all possible outcomes for this experiment and also list the sample space. So, all right, so we're at this fair, we're at this carnival, and at the start, we're going to roll the dice. And there's three sides on this dice. It's a weird dice, right? You could roll a one, you could roll a two, you could roll a three. Okay. Now, after you roll, so let's say you roll a one, okay? Then you're going to spin the wheel, and there's three outcomes you can get for that. You could get red or yellow or green. Now, if you roll a two, you still could get a red, yellow, or green. And the same thing with a three. You could also get a red, yellow, or green. Okay. All right. So, uh, let's see. Red, yellow. Okay. So the sample space is all possible outcomes. Okay. So um, if we roll a one and spin a red, we would mark it as one red. Okay. So that's what this tree diagram does, is it makes it easy for you to write out all the possibilities. Okay. So two red without missing anything, without repeating anything. Two green, three red, three yellow, and three green. Now, I will point out that tree diagram is going to break down pretty quick if we, start doing like larger things. So like if we rolled a six-sided die two times, six times six is 36. There's 36 possible outcomes. That's a lot to list. It's not too bad, okay? But if you rolled a six-sided die three times, that's 216 possible outcomes. That's just too much, right? So we're going to try to keep our sample spaces a little small, but uh, we'll see that on the next page. One of the answers is like huge, okay? Sample spaces grow pretty fast. Anyway, so these are all of our possible outcomes. I'm going to skip this one. So let's talk about part C. The events spinning red and tossing an odd number. Are those disjoint, not disjoint, independent, or dependent? So I want to first point out that this should have been two different problems. Disjoint and not disjoint, those are uh, you know, a separate discussion compared to independent versus dependent. Okay. Um, Something can be disjoint and dependent at the same time. Okay. So it says circle one, so you just need to circle one of these. Okay. But I'm going to point out some of them as we go. So I apologize. I didn't make the question. I did do the questions on the midterm. So if you see something like this, I'll have it split. Okay. Anyway, spinning red and tossing an odd number. So disjoint means that they cannot happen at the same time. At the same time. Okay. Uh, you may have in other statistics classes, you'll hear this called mutually exclusive. It's the same thing. Okay. Cannot happen at the same time. And so not disjoint means it can happen same time. Now, when I say same time, I don't mean like you roll the dice and spin the wheel with one hand and roll the dice with the other hand. I mean like for one game, right? You roll the dice and then after you get your result, you spin the wheel. Okay. So it's not necessarily the same time in like time, like on your watch, but like the same result, same game. Okay. So Kelly says these are not disjoint. Okay. And I agree with that. Can you spin a red and also at the same time toss an odd number? An odd number, so could be a one or a three. So yeah, you could get one red, one R, or you could get three R, right? Three red. Okay. So these two would be the same game. So yeah, it's not disjoint. Now, independent and dependent is a different topic. Okay. Independent means that uh, the first the first result does not affect the other. So uh, first result or any of the results, well, we'll say the first result does not affect or influence or change the other. Okay. Um, and then if it's dependent, then that's the opposite. Yes. So dependent would be one result changes the other. Okay. One result changes the other. Okay. So in this case, let's say that I spin a red. Okay, good job. Got it. Is that going to change the chances that I get an odd number? It's not. Okay. So these are in this case are independent. Okay. The number you get on the die does not change uh, your chances of getting a result on the wheel. Okay. So dependent would be, if I had three different wheels and one of the wheels had no yellow and one of the wheels had like a lot of red, okay, and very little green or yellow, and the die result told me which wheel to spin. Those would be dependent, okay? Because if I rolled a one, then it's possible that number one means, okay, spin the wheel with no yellow. So in that case, one yellow can't happen, okay? So we'll see. We'll talk more about independent, dependent. We'll talk more about disjoint and not disjoint quite a bit on this worksheet. You only need to circle one of these, by the way. If you circle both, great job. If you circle one, that's also great. If you circle one of the wrong ones, well, don't do that. All right, next. Tossing less than a two and tossing at least one. So less than two would be a one, right? You'd have to, in this case, tossing less than a two is, roll a one. Tossing at least one. At least one means one or more. So one at the least, and then you could go up from there. So one or higher. Well, all of these are one or higher. One, two, and three, those are all one or higher. So really this is roll anything. Toss any, so roll any number. So are these disjoint or not disjoint? Can you roll a one and also at the same time roll any number at all? Yeah, yeah, certainly, right? If you roll a one, you rolled a number. So good job. Yes, Mike's got it. Not disjoint. Okay. Uh, independent versus dependent. I'm not going to talk about that one for this particular case. It's mathematically speaking, they're independent. I'm not going to worry about that. We'll talk more about independent and dependent in a little bit. This one's a bad example. Yeah, this is a poorly written question. I apologize. Okay, moving on. Compute the probabilities, blah, 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 blah. Watch out for the word or in statistics class, okay? Um, in statistics, the word or is different from or in English, okay? At the bottom of page 254, there's a list of probability rules. There's 5 of them here. Okay. So for when you have or, you need to pay attention to whether they are disjoint or not. Okay. And that's going to change whether you're using rule 1 or rule 2. Okay. Um, so this one is going to be, let's see, getting a 3 or yellow. Those are not disjoint. So this will be rule 2. Rule 2. And then this one, probably of not getting red, this is rule 3 on that page. Okay. Um, yeah. So when you're doing disjoint events, probability of E or F, you just add them together. Here's E plus F, done. Okay. That's if they're disjoint. Okay. If they are not disjoint, then it's a similar, it's probability of E plus probability of F minus the probability that E and F happen at the same time. Okay. We're not removing this. This is we have to subtract the overlap. Okay. Um, and I'll point that out as we go. But this is, P of E or F, and this is also P E or F. Okay. Both of these are the same depending on whether it's disjoint or not. Okay. So we'll talk more about that as we go, but like I was saying, or in statistics is different from or in English. So like if I ask my daughter like, um, what do you want for dinner? Do you want pizza or cheeseburgers? It's understood that she can't pick both. Okay, it's understood that she can pick cheeseburgers or pizza, one or the other. If she said both, then we'd be like, I'm not going to buy you both. You're not going to eat all that. Okay, so, but in statistics, when we say or, you could ask, it could be this, it could be A, or it could be B, or it is possible it could be both. Okay, so, all right, let's move on. Question I. The probabilities found above are classical, empirical, or subjective. Classical means it's theory. Okay, it's you know doing a bunch of formulas, right? Empirical is you have an experiment or actual data. Okay, observational data, experimental data. Okay, and subjective is made up. Okay, so so what do we have in this case for this game here? What do you guys think? Yeah. Thank you, Kelly. Classical. Yes. It's classical because we haven't actually played the game. We came up here and we listed out the sample space. Did I actually get a one red and a one yellow and a one green? No, I didn't, right? We're going to play this game once. We're going to get one of these results, okay? And or maybe you get the same result twice, or maybe you do get all of these different results if you play the game, over and over and over. But we didn't actually play the game. We didn't actually do the experiment. Okay. So all we've done is discuss the possibilities. Okay. So that is classical. That is theoretical. Okay. We haven't actually rolled the dice. We'll see examples later on this worksheet where we are looking at real data. Okay. Uh, yeah, looking back at the data that we already did would make it empirical. That's correct. So, Mike, if we had played this game, let's say 10 times, and I list out my results, that would be empirical. Okay. Um, okay. So empirical is actual data. Okay. And the last one is subjective, which is made up. That's not to say that it's useless. It's not to say like it doesn't matter. Okay. So an example of subjective would be like if my friend asked me like, hey, are you going to come to the party? And I'm like, I don't know. I'm 50-50. Is there actually a 50% chance that I'm coming and a 50% chance that I'm not? No, I just made those numbers up. But that doesn't mean that that's useless information. That is actually helpful. That tells my friend, okay, I might come, but don't rely on me, right? So maybe make sure there's enough food in case I do come, but also don't, rely that like, oh, he's definitely going to be there, right? Or, you know, I always say to my wife, she's like, "Did you, do this? Did you get it done?" And I'm like, I'm 90% sure I got it done. I'll double check. A bad memory. So, okay, but that, like I said, that doesn't mean that that's useless. Those numbers are useless, even though they are made up. I love subjective. Let's see if there's any subjective ones on here. Which of the following numbers cannot be the probability of some event? So, probability of X um, is going to give you a number, but there's only a certain range. So there are three answers here. The probability of an event has to be between 0 and 1. Okay. Um, so Mike's listed them out for us. 103%, that is bigger than 1. Okay. 1 is 100%. So that is no good. 4 divided by 2 is 2. That is also bigger than 1. And negative 0.67, that is less than 0. So that one is also no good. Okay. So when we're talking about probabilities or percents or relative frequency, right? We've talked about relative frequency. Those numbers have to be between 0 and 1. Okay. Between 0% and 100%. Okay. Kind of like, the coefficient of determination, which was r squared, right? That has to be between 0 and 1. All right. Let's skip past that. Let's do this one. The following table shows the probability distribution of blood types and Reese's factors. Sounds delicious. For a random sample of people living in Quebec. Okay. Um, so we're looking at blood types. So O positive, A negative. Yeah. Um, question B. Blood type is a qualitative, quantitative discrete, or quantitative continuous variable. Thank you, Jordan. It is qualitative. When we're talking about probability, most of the time, not always, but most of the time, we will be talking about qualitative data. Okay. Because if I asked you, so Gabby said she's blood type A. Okay. Is A plus B equal AB? No, you can't do math on that, right? There are numbers here, but these are not numbers. This is not blood types. This is how many people have blood type A. Okay. So, for a single person, A and B blood types are disjoint or not disjoint. So, can you be both A and B at the same time. Now, AB is not the same as A and B together, right? I don't, this is a different blood type. I don't know why they didn't just call it C, right? Actually, I also don't know why they're not in alphabetical order. Like, why is O first? But I think O is it's the universal donor or the universal receiver, right? So these are disjoint. You guys got it. Good job. Uh, so they cannot happen at the same time. Okay. If two events are disjoint, they are automatically dependent. We said a second ago that dependent means one result changes the other. So if I say I am blood type A, that automatically changes my chance of being B. It changes it to 0. It automatically affects that if I say I'm A, yes, I am, then that automatically says that the second event is affected. It can't happen. Okay. Now, if it was not disjoint, then it could be independent or dependent. Okay. Um, okay. For a single person, uh, A and plus blood type. So can you be A and plus at the same time? Yes, you can. So Gabby's got it, not disjoint. Yeah, so these are the A plus people. A plus, that sounds like the best, right? It's the grade you're going for, A plus. Uh, independent or dependent. So this one's tricky. If I say yes, I'm type A, does that change the chances that I am a plus? So independent or dependent, what do you think? So you'll notice that if I'm A, there's a much higher chance that I'm a plus than if I'm a negative. Okay. So it does change it. It is dependent. Okay. The result, getting the first result, affects the probability that I am the second result. Okay. These are not equal. All right. And again, you only need to circle one of these. So if you're like, I don't understand, then that's okay. Just circle that one. Okay. Um, yeah. I didn't write these questions and I apologize. They're poorly written, but it's basically two questions in one. For two related people, the event's O plus for the first person. So maybe this is a mom and a son or a brother and a sister, right? If the first person's O plus, the second person is also O plus, disjoint or not disjoint? Yeah. These can happen at the same time, which means they are not disjoint. Okay. The mom can be O plus and the son can be O plus. That's fine. Okay. Now, independent or dependent. So if the mom says she's O plus, is that going to change the chances that the son is, or the brother or sister, or whatever? These are related people, right? Independent or dependent. These are dependent because if the first person says they're O positive, that means there's a higher likelihood that the second person also is because we know that blood types are genetic. Okay, so if you're related to an O plus person, you have a higher chance of also being O plus. For two unrelated people, so me and my friend, can we can so let's do disjoint and not disjoint. So can I be type A and they are also type A? So disjoint or not disjoint? Yep, Ryan's got it. Not disjoint. I agree. Yep. These can happen at the same time. I can be A and some other random person that I've never met can also be A. That's okay. Independent or dependent? Independent. Yep, you guys got it. If I am A, that doesn't change the likelihood that my friend is A, right? Unless this is a friend I met donating blood to them, I guess. But no, yeah. So independent. Okay. My answer does not affect their answer. Okay. You guys are good on that. Awesome. All right. Page 392. We're continuing on with blood types. So hold on to that. Choosing one person at random, find the probability that that person has any of these things. So probability is a fraction. It's the number of wanted outcomes divided by the total. Okay. We want 4 decimal places for these. Okay. So don't do it as a fraction. When we were looking at the classical answers over here, it says give it as a fraction. If you give it as a decimal, that's probably fine. Okay. But here I do want it as a decimal. Um, okay, so uh, this one right here is an or. So I said earlier, be careful with ors. So page 254 at the bottom, there's a list of rules on probability, okay? So this one is an or, so it's either going to be rule 1 or 2, okay, depending on whether these are disjoint or not, okay? Not type A, that's going to be rule 3 on the bottom here, complement rule, which just says the probability of not something is just 1 minus the probability that it does happen, okay? So the probability that I roll a 3 on a 6-sided die is 1/6. Probability I do not roll a 3 on a 6-sided die is 5/6, okay? It's just 100% minus the probability I did, okay? So this one and is easy. You just look where they're overlapping. There's no rule for this. Here's another or. So again, be careful with this. This is going to be rule. This one's going to be rule 2. This one I believe is rule 1. Okay. They're both or. It's because one is disjoint and one is not. Okay. Um, Choosing 3 people, unrelated, okay, so independent, okay. Find the probability that all 3 have O positive. So this will be rule 4 on that page because these are independent situations. So multiplication for independent events, so the probability that this person and this person and this person and so on, you just do each one separately and you multiply them together, okay. Probability none of them have AB. That's also rule 4. This one's the tricky one. Rule 5. You have 3 people. Find the probability that at least one person is A negative. Okay. Rule 5 is crazy. Rule 5 is probability that at least one event happens in N tries. Okay. So probability of at least one A negative in, how many was it? 3 people, 3 tries. Okay. So we're going to do this one right now. So probability of at least one A negative in 3 people. Okay. At least one means 1, 2, or all 3 are A negative. Okay. All right. So it is 1 minus, it's this crazy formula right here. 1 minus the probability of not E to the power of N. What the heck? All right, open parenthesis, probability not A negative, close 2 parentheses, and then raise it to the power of 3. So probability of 1 minus open parenthesis, 1 minus probability, excuse me, 1 minus open parenthesis, probability not A negative, close 2 parentheses, and then our N is the number of people we're looking at, or the number of dice you roll, or the number of, whatever, okay? Okay. This problem is kind of 2 problems in one. I need to calculate this part right here first. Probability of not A minus, not A negative for a single person, okay? And then we're going to multiply it 3 times, okay? That's what the cube, that's what the 3 up there is. So I'm going to come down here and I'm going to calculate probability of not A negative equals 1 minus the probability that a person is A negative. That's rule 3, okay? Which is 1 minus probability of A negative. Probability of A negative. So A negative is 96. There are 96 people that are A negative. That's what I want. 96. What's my total? Total of the total. Altogether, total is, yep, 1363. That's my total people. Total sample. Okay. So I can calculate this 1 minus 96 over 1363. I don't need any parentheses around that. Minus 96 divided by 1363. 0.92 how many digits? 4 digits? 9296. Okay. All right. So this is 0.9296. That's what I'm going to plug in right here. So it's going to look like this. 1 minus, parenthesis, 0.9296, close my parenthesis, and cube it. Okay. Technically, I don't need those parentheses, but it makes sense if I put them in there. So this circle right here and this circle right here, that's this guy, right? All right. Now I'm going to plug this into the calculator, see what we get. Minus 0.9296. All right, to do a cube, you hold the shift button and you hit 6 on your keyboard. There's a little up arrow, and then you hit a 3, and you'll notice that it bumps that 3 up. That's now cubing it. And we hit enter, and I get a final answer, 0.1967. That's my answer. Okay. We'll do another one of these at least things on the next page. Okay. It's crazy, right? So as long as you break it down into steps, it's basically two problems in one. You do, the probability that the thing does not happen, and then you plug it in to the formula. Which probabilities above are unusual? So on page 253, we had some rules for how to tell if an event was unusual. Unusual rules of thumb were if your z-score is outside of 2 standard deviations, so bigger than 2 or less than -2 away from the mean, we say that that's unusual. And that's because 2 standard deviations is 95% of your data. So outside that is 5%. Okay. Now every z-score has a corresponding probability that goes with it. And so we are not looking at z-scores here. We're looking at the second bullet point. Yep. You were right, Gabby. In this case, probability or percent or proportion. If your probability is less than 5%, we consider that unusual. So you want to look at probability of X is less than 5%. So for question N, is that less than 5% or bigger? This is bigger. Yep, this is 19%. So this is not unusual. Okay. Anyway, we haven't finished, so we'll come back to those. The probabilities that we found for all of these, we didn't actually do any yet. We did that one. Are these classical, empirical, or subjective? Rise says empirical. Yeah, definitely empirical in this case, right? We have legitimate data where, we actually, got 1,363 people in Quebec and actually measured their blood type. Okay. So empirical for sure. All right. Probability distribution here shows the primary home heating fuel in New Mexico in 2023 by type, according to data from the US Census. All right, so the probabilities of the different home heating fuel types must add up to what? So you don't need to add them up. If it is a probability distribution, then we know that they total up to 1. Yep, you guys got it. 100%. Yep, these should add up to 1. Uh, the type of residential heating is a which kind of variable? Thank you, Mike. Yeah, qualitative, right? Don't get tricked by these decimals, right? It's not continuous just because you have decimals. Those are the probabilities. Whenever we're dealing with probability, we are most of the time dealing with qualitative data. So if I asked a person like, how do you heat your home? They're not going to give me a number. They're going to say electricity. That's a word. That's qualitative. It's a category. And this is just counting how many people, what probability, how many people use that same type. Okay. Um, for one household, the event's primary heating fuel is electricity and primary heating fuel is wood. Are those disjoint or not disjoint? I got a not and I got a yes. I need a tiebreaker. Yeah, this one's a little tricky because can you heat your house with electricity and also heat with wood? Yeah, you can, but this is the key word is primary. Primary is the main way that you use it. The you might use electricity mostly and just have wood, like a wood fireplace that you use sometimes. So these are disjoint. Okay, primary heating is the main thing. Okay, um, even if these were equal, they're not going to be. You're not going to count that same person twice. Okay, you're only going to list that person one time. So these are disjoint. If they're disjoint, that automatically means that they are dependent, okay? Because if your main way of heating is electricity, then that means that you cannot also have your main way be heating with fuel. So this answer, your answer to this does affect your answer to the second event, okay? For two random unrelated households, okay? So uh, the event's primary heating fuel is electricity and the primary heating fuel is wood. Disjoint or not disjoint? Yep, Raya's got it. These are not disjoint. Okay. So I can have electricity and then my neighbor can be wood. That's fine. Those can happen at the same time. Independent or dependent, we said that these are unrelated households. So I agree with you that these are independent. Okay. So whatever I pick does not affect this other guy who lives on the other side of town. Um, all right. Uh, This is the word or. Pay attention to the word or. Are we using rule 1 or rule 2? Depends on whether they are disjoint or not. If you select random households in a mix, what is the probability that not, so not is rule 3. Okay, page 254. If you select two random unrelated households, what's the probability that the primary heating fuel for both households is electricity? This will be rule 4. You just multiply them together. You select two random unrelated households. What's the probability that the primary heating fuel for at least one household is wood? So this is rule 5 again. Okay. So in this case, where is it? And I'm looking at the wrong page. So at least one wood, so our E in this case is wood, in two houses, so my N in this case is 2. So it's 1 minus the probability of not wood, close my two parentheses, and then raise it to the power of 2. But for now, we are going to stop the recording. We'll go back, jump to back to page 390 and go over the ones that we skipped.